Alright, so now we're going to look at what happens if we have an op-amp with finite gain and bandwidth. Alright, as I said before, we want the gain of our amp to be infinity. So we'll say we want the gain A to be infinite. But in reality, we know that the gain of our op-amp is going to have some frequency dependence and have some finite value. So we can say in reality our gain is going to be a function of frequency, where we have some DC gain, and we'll assume for the time being that we have a single pole at high frequency. So if we were to plot this on a Bode plot, just the magnitude, we'll start looking at phase in a bit. So we plot this versus log of omega. This is our function A of S, magnitude. We would see that from DC, the amplifier would have a gain that was equal to 20 log of A0. And A0 for the op-amp we've been looking at, of course, is GM times RO2 in parallel with RO4. So that would be that value. Now, it would be flat until we reached our pole frequency, omega p. And remember, our pole frequency, omega p, was equal to 1 over RO2 in parallel with RO4 times our total load capacitance, CL prime, from the prior slide. At this point, the gain would roll off. It would have a slope of minus 20 dBs per decade. And so what we're fighting against, first of all, is that we want this gain to be infinite, so we need to try and make it as big as possible. It's difficult to do in a single stage. But we're also fighting against the fact that if we change our load, we change the bandwidth of our circuit. And that's not good. Now, at the frequency where the gain crosses the 0 dB point, this is where the gain is equal to unity, we call this frequency omega t. Now, if we write an expression for our operational amplifier, the gain at omega t, we can say that the gain at j omega t is equal to our DC gain, A sub 0, divided by the square root of 1 plus omega t divided by omega p squared. So we're looking at the magnitude of the gain. Now, what we're going to do is assume that omega t, our transition frequency, is at a much higher frequency than our pole frequency. So we're saying omega t over omega p is much, much larger than 1. And if we do that, then we can ignore the 1 here. And we can simply say that A sub 0 divided by omega t over omega p is equal to 1. So this is the gain at omega t is equal to 1. And from here we would be able to say that omega t is equal to A sub 0, our DC gain, times our pole frequency. This is, in an amplifier, what's called the gain bandwidth product. On a specification sheet you might see gain bandwidth product. What's interesting is that for any operational amplifier that you pick up off the shelf, it will have a gain bandwidth product, and no matter what the configuration you hook your operational amplifier up in, the gain bandwidth product will always be a constant. All right, so we're going to look at a few different examples of operational amplifiers tomorrow, in the next part of the lecture, I should say, trying to increase the gain of the operational amplifier. That's going to fix this first problem. We want this gain to be increased and approach infinity. And then we'll start looking at the frequency response, trying to see what happens when we do this.